So let's start with the actual syllabus of gravitation. So let's see Kepler's laws. What are those Kepler's three laws? The first law is known as law of orbits. What is law of orbits? Every planet revolves around sun in an elliptical orbit. Every planet revolves around sun in not circular orbit, it revolves in elliptical orbit. Okay, so like this, having sun at one of foci of the ellipse. So as we know, ellipse has two foci, okay, f1 and f2. So sun is at one of the focus, and earth and all other planets, they revolve in elliptical orbit. Okay, so now this ellipse has got two axes. So this one is known as the major axis, and there is one more which is known as minor axis. Okay, so now the semi-major axis, half of the major axis, is it lagging? What is semi-major axis? It is half of the major axis. All right. So this is Kepler's first law. Every planet revolves around the sun in an elliptical orbit. So Kepler had studied Tycho Brahe's data, and he gave us this law. Okay. Then second law is law of areas. So what is law of areas? Line joining position of sun to the position of planet sweeps out equal areas in equal intervals of time. Okay. So if you join any planet, for an example, Earth, so center of this planet to center of sun, you will get a line, and then that line will move through equal areas in equal intervals of time. Okay. So suppose Earth moves from position A to position B in some time t. When this line is moving through this much area, okay, this shaded area, then suppose it moves from C to D. Okay, so this is C. Oh. Suppose Earth moves from C to D in same interval of time, then here the position vector of Earth, it sweeps out this much area. Sweeps out means it moves through this much area. Okay, so now if time taken to move from here to here is equal to time taken to move from here to here, then this area will be equal to this area. This is Kepler's second law. This is known as law of areas. Okay, so now this law of areas is actually based upon the law of conservation of angular momentum. Okay, so see, if you consider sun and earth, now earth is moving because of the mutual gravitational force of attraction, right? So there is no external force on this system, and if there is no external force, what does it mean? It means that the angular momentum of earth will remain constant. Okay, yes, no? Okay, now see, earth moves through equal areas in equal intervals of time. So now if you consider this much area, okay, suppose earth moves from here to here, consider very small movement. Okay, so this arc is almost as equal to the actual displacement, and now you have this triangle. Okay, how will you find out the area of this triangle? That is the area through which earth is moving. It is half of base into height. So if this triangle is very small, you can say that this is the base, RT is the base, okay, radius at time t is the base, or position vector at time t is the base, and the delta s is the height. So half of base into height is the area. Now if you take rate of change of area with respect to time, what do you get? So just divide this by time, okay, time delta t, through which in which it moves through this much distance. So delta s by delta t will give you v. So you get half of r into v. And now if you just multiply and divide by m, what do you get? So numerator you have mvr. What is mvr? Mvr is angular momentum. Okay, mvr is angular momentum, and in denominator you have mass, which is constant. So now if rate of change of area with respect to time is constant, not rate of change of area, the area covered with respect to time, if it is constant, that means that L is constant, angular momentum is constant. Okay, so if angular momentum is constant, the area covered in equal times will be equal. Area covered per unit time is a constant. Is this point clear? You have to remember this, that law of areas is consequence of what? Law of conservation of angular momentum. Okay, there can be a direct question. All right, so then not just in this case, wherever you have radial force meaning you have one body, it exerts force on another body and forces along the direction of line joining two bodies, that is radial force, then torque will be zero. Okay, because tau is r bar cross f bar, which is r into f multiplied by sine theta. Here theta is either 0 or 180 degrees. Okay, if it is attractive force, it will be 180 degrees. If it is repulsive force, it will be 0. So then torque is 0 for radial forces, and therefore angular momentum is conserved. Okay, so this will happen in case of radial forces. So you have any kind of circular motion. For an example, you have a stone tied to a string. Again, tension in the string is radial force. Okay, in that case also, if there is no external force and tension remains constant, so what will happen even if tension changes? Okay, so what will happen? There will be no torque, and therefore angular momentum will remain conserved. Okay, then this is okay, angular momentum will remain conserved. Then you can consider example of gravity. Okay, in case of gravity, again angular momentum is conserved. What can be another example in which there can be this type of question? In case of you have atom and an electron, electron revolving around atom, it moves because of what? It revolves because of the electrostatic force. Okay, so that is also radial force. So torque is 0 and angular momentum of electron is conserved. This is clear? Okay, good. After that, next is law of periods. So that is square of time period of planet. Okay, planet's orbit around the sun, it is directly proportional to cube of semi-major axis. Square of time period is directly proportional to cube of semi-major axis. So what is semi-major axis? So if you consider the farthest position of a planet and the shortest position, then shortest is A, farthest is B. If you join those two positions, you will get a line passing through the focus, both foci of ellipse. It is known as semi-major, sorry, it is known as major axis. Take half of that. Why take half? Because it's the average radius. Okay, it's the average radius of planet's orbit. So if you take semi-major axis, then square of time period is directly proportional to what? Cube of the semi-major axis. Or we can say square of time period is directly proportional to cube of average radius of planet. Okay, this law is clear. So now let's come to the Newton's law of gravity. So what is Newton's law of gravity? Newton's universal law of gravity. Every body in the universe attracts every other body of the universe with a force which is directly proportional to mass of the two bodies and inversely proportional to square of distance between them. You have two masses, m1, m2. Okay, then there will be gravitational force between these two masses. That force will be always an attractive force, and it is directly proportional to their product, okay, product of two masses, and it is inversely proportional to the square of the distance between two. So F is proportional to m1 m2 upon r square, and if you remove the proportionality sign and put an equality sign, constant will appear. That constant is known as universal gravitational constant, right? So this constant is same for force of attraction between any two bodies in entire universe, okay, in solar system and beyond, you can say. All right, so this is Newton's law of gravity. F is equal to g times m1 m2 upon r square. This formula, of course, we have to remember. And we can write this formula in vector form. How can we write it in vector form? So see, magnitude will be same. So suppose you have this mass, you have this mass. So position vector of this mass is r1 bar, position vector of this mass is r2 bar, and now you have this vector, this is r12 bar. What is r12 bar? It is r2 bar minus r1 bar, okay, which is directed like this. And now you want force on m2 due to m1. Force on m2 due to m1, it is written like this: F21 bar, force on 2 due to 1, force on 2 due to 1, okay. So it is g m1 m2 upon r12 square multiplied by, here you will have minus of r12 bar, r12 cap, sorry, okay. So to show the direction, we'll use unit vector. And what will be direction of that unit vector? So force on this mass due to this mass is not directed like this. If it was like this, it would be repulsive force, okay. This mass is pulled by this force, and therefore it is in opposite direction as that of r12 bar, right? Therefore we have negative sign. This is clear. These are very simple points. So now let's see some questions, simple questions. The kinetic energies of a planet in elliptical orbit about the sun at positions A, B, and C are Ka, Kb, and Kc respectively. AC is major axis and SB is perpendicular to AC. SB is perpendicular to AC at the position of sun as shown in the figure. Then tell me which one is correct. Okay. So here we have to remember one thing: speed of planet will be highest. Speed of planet will be highest when it is closest to the sun. Why? Because we said that angular momentum is conserved, right? L is conserved. So what is L? L is mvr. Okay. V into r is constant. Okay. L is equal to mvr, right? So m is constant. V times r is constant. Okay. Because mass is constant, L is constant means V times r is constant. So if V increases, sorry, if r increases, V will decrease. If r decreases, V will increase. Okay, because V multiplied by r is constant. If you increase r, V will decrease. If you decrease r, V will increase. V is inversely proportional to r. Okay, you can call that constant C. So V will be equal to what? C upon r. And now can you tell me velocity is inversely proportional to r? At what point will it be maximum? At point A. Then So at A it is maximum, then it's B, then it's C. So which is the option? No, this is minimum, no? It's option B, right? Okay, yeah. So at A kinetic energy is maximum, then it's point B, after that it is point C. Okay, this is because of conservation of angular momentum. Let's see next one. A planet moving along an elliptical orbit is closest to Sun at distance r1 and farthest away at distance r2. If v1 and v2 are linear velocities at these points respectively, then the ratio of v1 to v2 is, tell me. Very good. It will be r2 by r1 because v1 r1 will be equal to v2 r2. Product of v and r is constant. So v1 upon v2 will be equal to r2 upon r. So it is option B. Next one, the figure shows elliptical orbit of a planet M about the Sun. Shaded area SCD, this one, is twice the area SAB. If T1 is the time for planet to move from C to D and T2 is time to move from A to B, then tell me. No, no, no. It is R cube. Okay. T is directly proportional to area. Kepler's second law. Kepler's second law, time period is directly proportional to areas. Sorry, not time period, time covered. Time taken is directly proportional to area. Okay. So time to move from A to B will be half of time to move from C to D, right? So T2 is time to move from A to B. It will be half of time to move from C to D, which is T1. Or I can say T1 is equal to 2 times T2, right? Because this area is half as that of this area, and area is proportional to time. Next one, the period of revolution of planet A around Sun is 8 times that of B. The distance of A from the Sun is how many times greater than that of B from the Sun? Tell me. Here you can use B square is proportional to R cube. Okay. This is 2. Let's check. TA by TB square will be equal to RA by RB cube. The period of A around Sun is 8 times that of B. So TA by TB is 8 because TA equals to 8 TB. 8 TB. Okay. So this is 8. 8 square is 64. 64 is RA upon RB cube. Okay, now take cube root on both sides. So RA upon RB is equal to cube root of 64. So how much is cube root of 64? It's 4, right? Therefore, RA equals to 4 times of RB. So option A. Okay. This kind of question is repeated. See next one. The distance of two planets from Sun are 10 raised to 13 and 10 raised to 12 meter respectively. The ratio of time periods of planets is, tell me. Again we'll do same thing. Okay. T1 by T2 square is equal to R1 by R2. So I will directly write 10 raised to 3 by 10 raised to 12 cube. Okay. So this is 10 cube, or you can say 1000. This is T1 by T2 square. Therefore, T1 by T2 will be square root of 1000. How much is it? 10 root 10. Right. So this is the answer. Okay. Next one. Planet is moving in an elliptical orbit around the Sun. T, V, E, and L stand respectively for its kinetic energy, gravitational potential energy, total energy, and magnitude of angular momentum about the center of force. About the center of force, which of the following is correct? Tell me. Angular momentum is conserved, but direction of vector L changes continuously. Actually, direction of vector L also remains constant. Okay. Its answer is option C. E will be negative. Okay. They have asked which one is correct. So E is always negative is the answer. Okay. So we'll see this. We'll see this that the total energy will be negative. Okay. In any bound system, total energy will be negative. Okay. In case of any bound system, total energy will be negative. Right. Just remember this. For this thing also, for atom also, total energy will be negative. Okay. This is the answer. L is conserved. See, for an example, if you take this, suppose a planet is moving in an ellipse. Now, L is conserved in magnitude. And if you find its direction, so this is suppose R, this is velocity. Okay. This is R, this is V. So now you move to any position. What will be direction of L? L is equal to M multiplied by R cross V, because it is R cross P. P is linear momentum, which is M into V. Okay. So now it is directed along vector product of R and V. So do vector product. This is R, this is V. It is moving in anti-clockwise sense, right? So if you are stretched, sorry, if you keep your right hand in direction of R, move fingers towards V and stretch the thumb. Stretched thumb will be upwards. You do it here. Let the planet move here. Let the planet move here. Okay. Here also R will be directed like this. V will be directed like this, tangential to the path. So this is R, this is V. Do R cross V. Again, you will get vertically upwards direction. So the direction of angular momentum also remains conserved. Is it clear? Okay. So its answer is option C, that energy will be negative. This is true for any bound system. The total energy will be negative. Okay. If you want to remove it, if you want to, suppose Earth is revolving around Sun. Now you want to remove Earth from there. Okay. You want to move it to infinity. Then you will have to supply some energy, and at infinity the energy will be zero. So now you want to put some energy, means its energy is negative. Got it? Yes, no? Okay. We'll see this separately when we'll see energy. Okay, but for the sake of this question, this is the argument. All right, let's see next question. Two astronauts are floating in gravitational free space after having lost contact with their spaceship. The two will. Tell me. Move towards each other, move away from each other, will become stationary, keep floating at the same distance between them. They are floating in gravitation free space. If there is no gravitation, okay, so now what will happen? Gravitation free space means there is no external gravitation. Okay, it means that there is no big planet or star whose gravitational field would be there. But these two astronauts, they will attract each other, right? This is gravitation free means there is nothing, no planet, no star, okay, whose gravitational force would be there. There is nothing like that. But these two will exert gravitational force onto each other. So what will happen? No, if they exert gravitational force on each other, if both of them attract each other, they will move closer to each other, right? They will move towards each other. No, there is no external gravity, but these two will attract each other. So they will move towards each other. All right, let's see next. Two spheres of masses small m and capital M are situated in air, and the gravitational force between them is F. The space around masses is now filled with the liquid of specific gravity 3. The gravitational force will now be. Tell me. Okay. See, the gravitational force doesn't depend on the medium between two objects. Does it depend on medium? It doesn't depend. Okay. It does not depend. So it will remain constant. Okay. So it's option B, right? Okay. Let's see next one. If the gravitational force between two objects were proportional to 1 by r and not as 1 by r square, where r is distance between them, then particle in circular path would have its orbital speed v proportional to. Tell me this one. This is simple. They say that suppose a gravitational force is proportional to 1 by r. Okay. Then particle in circular path. So suppose Earth moves along around Sun in circular path. So the centripetal force is provided by gravitational force. Okay, gravitational force. And question is if it is proportional to 1 by r. So suppose it is constant upon r, proportional to 1 by r. Then what will happen? What will happen to the speed? So centripetal force is mv square upon r. R and r will get cancelled, right? Mass is constant, so v square will be constant, and therefore speed will be constant. So which is the answer? It's option B, independent of r. Okay. All right. Then let's see this point. The gravitational force due to a shell. Okay. So suppose you have a shell like this. Now, suppose you have a shell like this. If you have some mass outside of that shell, so now you can consider small pieces of the shell. Let's suppose this small piece is dm, this small piece is dm. So this small piece will attract this mass in this direction. This one will attract this mass in this direction. Okay. Now you can resolve this force df due to this small mass, this mass element, along two perpendicular directions like this one and this one. And you have considered same amount of mass here. Okay. Whose distance from this point is equal, right? This distance and this distance is equal. Then it will also exert same amount of force, but it will be in this direction. And you resolve that force also along the perpendicular, two perpendicular directions. So one will be in this direction, one will be in this direction. Okay. So suppose this angle is theta. This angle will also be equal to theta, and therefore now these components will be df sine theta, df sine theta. They are equal and opposite. Okay. And therefore force due to this mass and this mass is in this direction only. So these two components get cancelled out because they are equal and opposite. So net force due to these two masses is towards the center of the shell. Okay, is this thing clear? Now we can consider such small pieces, okay, one on this side and one on this side, whose distance from this mass will be equal. So forces due to those two will also be, sum of forces due to those two will also be in same direction. Okay, so that means due to whole complete shell, the force on this mass, which force? The gravitational force, will be in this direction only, because the perpendicular components of force will get cancelled out. Okay, so if you have a gravitational, if you have a shell, the gravitational force due to that shell will be always directed towards the center of shell. If this body is outside the shell, if the body is outside shell, then gravitational force due to shell on that body will always act towards the center of the shell, and that force will be equal to g into m upon r square, where capital M is mass of shell and small m is mass of this body. And what is r? It's not this distance or this distance, it is distance of center of shell from this mass. Is this point clear? Now suppose you have this mass is kept inside of shell. Okay, this mass is kept inside of shell. Then the gravitational force on this mass due to the shell will be equal to 0. Okay, gravitational force on this mass due to the shell will be equal to 0. How? So let's consider some area over here, area of the shell. Consider this area. Join this area, okay, join the boundary of the area with this mass, with this point. So suppose this mass is at distance r1. Okay, mass is at distance r1 from this area. Now you extend that r1, you will get this point. Okay, you extend this line, you will get this point. So just like that, if you extend these lines which you connected with this point, so if you just extend those lines, they will cut some area on the other side. So suppose this area is dA1, this other area is dA2. Okay, so now this distance of this area from this mass, we suppose r2. Okay, so forget about rest of the shell, concentrate on this area and this area. So what will happen? Now this area has some mass, so it will attract this mass by gravitational force, and this area also has some mass, so it will attract this mass by means of gravitational force. Okay, and those two forces will be equal and opposite. Those two forces will be equal and opposite. Okay, so why will they be equal and opposite? Because the solid angle, okay, solid angle, this solid angle and this solid angle is same. Okay, if you recall, in first lecture we studied about solid angle. It is a cone, right? It is this area divided by this distance square, r square. So this area upon this r square will be equal to this area upon this r square. Okay, and what does that mean now? So mass of this area, mass is proportional to area because this is a thin shell, right? So mass of this, suppose surface mass density is sigma. Okay, it is total mass upon total area. So mass of this area will be sigma multiplied by this area, right? Mass of this area will be sigma multiplied by this area, if sigma is mass per unit area. Okay, so now see, force on mass m due to dA1 will be equal to what? G times m multiplied by that mass dm1 upon r1 square, and force on that mass due to dA2 will be G multiplied by m multiplied by dm2 upon r2 square. Okay, so these two forces will be equal because see, this is equal to what? Sigma times dA1 upon r1 square, and this is equal to sigma times dA2 upon r2 square, and dA1 upon r1 square is this solid angle, okay, this cone. dA2 upon r2 square is this cone. Okay, size of this cone and this cone is equal, and therefore these two forces are equal and opposite. Okay, force due to this mass, force due to this mass is equal and opposite. So net force on this mass m will get cancelled out. Is it clear? Yes, no? Okay. So therefore we can consider such areas on the complete shell, and the total force on this mass m due to all such areas, if you add all those areas, okay, masses of all those areas, then total gravitational force on this mass m, which is inside of shell, will be equal to 0. Okay, so we'll need this point. We'll need this point. Okay, when we prove gravitation, the acceleration due to gravity inside of Earth. Okay, and this thing is true for, suppose you have a charged spherical shell and you keep another charge inside that shell, then in that case the electrostatic force will be 0. Okay, this is clear. So now let's see acceleration due to gravity. Okay, so what is acceleration due to gravity? It is gravitational force due to Earth on any mass. Sorry, I'm sorry, what did I say? Okay, suppose you have this mass and this is Earth. Okay, this mass is here at distance h, away from Earth. This is Earth and this is some mass. So what will be weight of this mass? Weight of a body is the gravitational force on that body due to Earth, right? Okay, so weight can be written as what? mass of this body multiplied by acceleration due to gravity. Acceleration due to gravity, where? Acceleration due to gravity at this point, okay, at height h above the earth surface. That is weight of that object at that height, okay. So we can write this m times gh as equal to the gravitational force gmm upon r square, where capital M is mass of earth, small m is mass of the body, and small r is distance between mass of body to center of the earth, okay. So then now this m and m will get cancelled out. So what do we get? We get this formula, gh is equal to gm upon r square, okay. Gh is equal to what? Gm upon r square. What is small r? Small r is equal to capital R plus h, okay. So this formula is very important. Gh is equal to gm upon r square, small r square, which is capital R plus h square. Now if we consider this body on earth's surface, then how much will be h? H will be equal to 0, okay. H will be equal to 0. So put h equal to 0, you get acceleration due to gravity on earth's surface as gm upon r square, capital R square, because h is equal to 0, okay. So you get this one formula, gh is equal to gm upon r plus h square, which is acceleration due to gravity at height h. Gh is acceleration due to gravity at height h. On earth's surface you have g, which is equal to gm upon r square. You divide this with this, what will you get? Gm and gm will get cancelled out, and you get gh upon g is equal to r upon r plus h square, or you can say gh is equal to r upon r plus h square multiplied by g, okay. So you have any height, acceleration due to gravity at that height will be equal to what? Acceleration due to gravity on earth's surface multiplied by r upon r plus h square. This is the exact formula, okay. This is the exact formula. Is this thing clear? Now what we do is we find an approximate formula, okay. So here we expand this term binomially. So we take r common, we'll get this thing, and we expand it binomially. We use binomial theorem, and finally we get this formula. So for h, very small compared to r. This point is very important, that h is very small compared to r, okay. There will be several terms in the expansion, so we neglect higher power terms, and we are just left with gh is equal to g multiplied by 1 minus twice h upon r, okay. H is the height, r is radius of earth, g is acceleration due to gravity on earth's surface. Then acceleration due to gravity at height h is equal to what? The g multiplied by 1 minus twice h upon r, okay. So this formula is applicable when? For small heights, okay. This formula will be applicable when heights are small. So height is comparable to radius of earth. Which formula will you use? This is suppose formula 1. This is formula 2. Which one will you use if height is comparable to radius of earth? First one, okay. Simple rule of thumb is, if height is given in terms of r, that means if they say h is equal to r by 2, okay, h is equal to r by 3, r by 4, whatever, h is equal to r by something, h is equal to r divided by 2, r by 4, r divided by something, then you have to use, where did it go? then you have to use this formula. Okay, if h is given in terms of r, and now if they say h is equal to 10 kilometers, 1 kilometer, 20 kilometer, 100 kilometers, then you can use this formula. Okay, then you can use this formula. But now if they say h is equal to 3200 kilometers, which formula will you use? You will use first one, because radius of earth is 6400 kilometers. So now simple rule of thumb is, if r is up to 640 kilometers, okay, if r is up to 640 kilometers, you can use this formula. It will be fast. Okay, and you will get reasonably correct answer. If it is more than that, use this formula only. Okay, if h is small, h is smaller than 640 kilometers, use this formula, otherwise use first formula. Fine. H is 10% of less than 10% of r, you can use this formula. Okay, then let's move on to the acceleration due to gravity at depth d below the earth's surface. Here what we do is, we find out acceleration due to gravity in terms of mean density of earth. Now density of earth is not constant. Okay, it is different at different points. So suppose rho is mean density of earth, then in terms of mean density of earth, we find out acceleration due to gravity. So this is simple. See, we write g equals to gm upon r square. We already got this. Okay, then we put mass of earth as density multiplied by volume. Okay, mass is density multiplied by volume. And what is volume? The volume is 4 by 3 pi r cube. So if you just substitute this density multiplied by 4 by 3 pi r cube in this formula, what do you get? See, here I have substituted. We get 4 by 3 pi r rho g. Okay, we get 4 by 3 pi r rho g. And this thing is an important formula. Okay, so we have to memorize this formula. Acceleration due to gravity in terms of density, g in terms of density, is given by this formula, 4 by 3 pi r rho g. So where r is radius of earth, rho is the mean density, average density of earth. Okay, and for any planet, you can say the acceleration due to gravity in terms of density will be 4 by 3 pi r rho g. This formula is important. Okay, so using this, we can find out acceleration due to gravity at depth d, because if depth is d, then we neglect this mass. Okay, why? If some mass is here, okay, you can consider this as a shell. What will be force, gravitational force on this mass due to the shell? Zero. So we neglect all mass that is outside. Okay, so if some mass is here, we'll only consider gravitational force on it due to this much sphere. Okay, all masses which are outside of this point, they are irrelevant, because you can consider this thing to be made up of n number of shells. Okay, n number of shells, and the gravitational force due to all of those shells on this mass will be equal to 0. Okay, and now therefore the gravitational force will be only because of this sphere whose radius is r minus d. Okay, so just change r by r minus d, you will get gravitational acceleration g at depth d. So g at depth d will be equal to 4 by 3 pi multiplied by what will be radius? So it is r minus d. Okay, this much radius, r minus d. Okay, so same formula, 4 by 3 pi r rho g. What will be r? R minus d. Then you compare this acceleration due to gravity at depth d with acceleration on Earth's surface. Some things will get cancelled out, and what do you get? Gd upon g is r minus d upon r. That is, Gd is equal to g multiplied by 1 minus d by r. Okay, and important thing is there is no limit to this formula. At what depth can we use this formula? There is no limit. Okay, so just like height, just like acceleration due to gravity at some height, we have some formula. We have acceleration due to gravity at depth d also. But for height, there are two formula. Two formulae. For depth, there is only one formula, and this is not approximate. Got it? So this can be used for any depth. Is this thing clear? Okay. So now, if I want to plot acceleration due to gravity from the center of Earth onwards, okay, starting from center of Earth, what will be the value of acceleration due to gravity? If I plot that versus distance, here, see, we got g. I can say g at radius r will be 4 by 3 pi small r into rho g. That is, here, so inside of Earth, what will be my formula? 4 by 3 pi r rho g. That means g at r, which is inside Earth, when r is smaller than capital R. It is directly proportional to r, and that's why you have a straight line. Okay, that's why you have a straight line. And after this point, at small r equals to capital R, small g will be equal to gm upon r square. And after that point, g will be equal to what? Gm divided by small r square. It's inversely proportional to r square. Okay. So till this point, till small r equals to capital R, it's directly proportional to r. After this point, it's inversely proportional to r square. Okay. So this graph is very, very important. It is asked 2-3 times. Okay. This graph is important. It is asked, this graph itself, it has been asked 2-3 times at least. Okay. So is this graph clear? The variation of acceleration due to gravity versus the distance. Distance from what? Center of Earth. After that, let's see what is the gravitational field. So what is a field? It is gravitational force divided by mass. Gravitational force per unit mass. So let's suppose you have some mass, some object whose mass is m. Now there can be gravitational force acting on this mass due to various objects. So you add up all those gravitational forces. Suppose the total force is F, then the gravitational field at that point is equal to what? That total gravitational force divided by mass. Gravitational force per unit mass. Okay. So what is gravitational field due to Earth? So we know gravitational force due to Earth on any object of mass m will be equal to gmm upon r square, where small r is equal to capital R plus h, right? So now if we divide this by m, mass of the object, so gravitational force per unit mass is just gm upon r square. And what is that? It is equal to acceleration due to gravity, right? It's equal to acceleration due to gravity. So you can say this is another name for acceleration due to gravity if we are talking about the Earth, gravitational field of Earth. Okay. So gravitational field due to Earth is just gm upon r square. For everything else, it will be what? Total gravitational force at a point divided by the mass that you are keeping at that point. So is this point clear? Now let's discuss some questions based upon what we discussed yesterday. So let's see this question. Dependence of intensity of gravitational field of Earth with distance r from center of Earth is correctly represented by. So tell me, it is option B, because gravitational field is just acceleration due to gravity. Okay, next question. Which one of the following plots represents the variation of gravitational field on a particle with distance small r due to a thin spherical shell of radius r? Tell me. Again, option B, right? Because till distance r, the gravitational force inside the thin spherical shell will be equal to 0. Correct. It's option B. Next question. A body of weight 75 Newton moves from the surface of Earth at height half of the radius of Earth. Then the gravitational force exerted on it will be. Tell me what we can do. Very good. So W is equal to m times gh, right? So which will be equal to m multiplied by g into r upon r plus h whole square. Okay. And mg is given, the weight of body 72 Newton, okay, on surface of Earth. And if you take it to the height equal to half the radius of Earth, r by 2. So let's keep h equal to r by 2. So this is 72 multiplied by r upon r plus r by 2. It's 3r upon 2. So 3r upon 2, square of that, r gets cancelled, 2 by 3 square. Okay, 4 by 9. Right, this 2 will go. This 2 is in denominator of denominator. It goes in numerator. So it will be 2 by 3. 2 by 3 square is 4 by 9. So we have 72 multiplied by 4 by 9. What's that? 8 times 4, 32. Sorry. Yeah, it's 32. Option B, right? This is simple. Next question. If the mass of sun were 10 times smaller and the universal gravitational constant were 10 times larger in magnitude, mass of sun is 10 times smaller. G, let's call it G dash, is 10 times G. Which of the following is not correct? Tell me. Raindrops will fall faster. Is it correct or not? Okay. Why? Because G is increased. Therefore, small g will also increase. Okay. So raindrops, their speed depends upon what? The acceleration due to gravity, which is gm upon r square. So if g increases, that means small g also increases. So speed of raindrops will also increase. Suppose they are falling from some height h. So speed is equal to what? Square root of 2gh. So it depends upon g. Okay. Next, walking on the ground would become more difficult. Will this happen or not? So this is also correct. Time period of simple pendulum on Earth would decrease. It will decrease or increase? It will decrease. Okay. T is equal to 2 pi square root of L upon G. So if G increases, time period will decrease. And G on Earth will not change. So this is incorrect. G is changing. So it's option D, right? Next question. A spherical planet has a mass mp and diameter dp. A particle of mass m falling freely near the surface of this planet will experience an acceleration due to gravity equal to, tell me. Option A. Let's check. So it is g is equal to gm upon r square, and it is given in terms of diameter. Okay. So r is equal to d by 2. Right. So it will be gm divided by d square upon 4, and that 4 will go to numerator. Good. It is option A. Let's see next one. Imagine a new planet having the same density as that of Earth, but it is 3 times bigger than the Earth in size. If the acceleration due to gravity on the surface of Earth is small g and that of surface of the new planet is g dash, then now tell me. Four by 3 pi r rho g. Okay, g is equal to 4 by 3 pi r rho g, and this is for that planet, so let's suppose it is gp. Okay, so it will be rp, density of that planet. Okay, only these things will change. Rp is radius of the planet, rho p is density of the planet. And what is given? Same density as that of Earth, but it is 3 times bigger. So it is just 4 by 3 pi 3r 3r times rho into g. Okay, so 3 we can take out. So it is 3 times of 4 by 3 pi into r, radius of Earth, into rho into g. So this is acceleration due to gravity on Earth. Okay, so it is 3 times g. Gp is equal to 3 times g. This is a simple question. Okay, option D. Next one, the density of a newly discovered planet is twice that of Earth. The acceleration due to gravity at the surface of planet is equal to that at the surface of Earth. If the radius of Earth is r, the radius of planet would be. Density is given, rho p is equal to twice of the density of Earth. Okay, and acceleration due to gravity at the surface of planet is equal to that of Earth. The radius of Earth is r. What would be radius of the planet? So this is simple. Acceleration due to gravity on the planet is equal to acceleration due to gravity on Earth. So because it is in terms of density, we'll use this formula, 4 by 3 pi r rho g. Okay, just for the planet, I have put suffix p, and for Earth 4 by 3 pi r rho g. G gets cancelled, 4 by 3 pi, 4 by 3 pi gets cancelled, and then rho p is equal to 2 times rho. So if you put 2 times rho here, you have rp into 2 times rho is equal to r into rho. Okay, r also, sorry, rho also gets cancelled, and you get rp equals to r upon 2, right? So option D. Okay, so very simple. Next one, the acceleration due to gravity on planet A is 9 times the acceleration due to gravity on planet B. A man jumps to a height of 2 meters on surface of A. What is the height of jump by the same person on planet B? Tell me. Acceleration due to gravity on a planet is 9 times that of planet B, and man jumps to the height of 2 meters on surface of A. what is the height of jump by the same person on planet B? Okay, so see, suppose the man jumps, then we'll consider that V is same speed with which he's jumping. The initial kinetic energy is same, okay, on planet A as well as on planet B. And therefore, what I can say is VA square is equal to VB square. Why VA square? Because B is equal to root of 2GH. Okay, we want to find height. We are given with acceleration due to gravity. So this formula will do. Okay, because man will jump with the same kinetic energy. The energy of jumping on both planets is same, right? Then we can say it is 2 will get cancelled. So it is GA multiplied by HA is equal to GB times HB, right? And we want to find it on planet B. So HB is equal to GA upon GB multiplied by HA. And on the planet A is 9 times that of the planet B. So this divided by this is 9. Okay. It is 9 times HA. So 9 multiplied by how much is HA? 2. So 9 times HA, 18 meters. This is the answer. Is this clear? Okay. Next one. What will be the formula of mass of Earth in terms of G, capital R, and small g? So this is extremely simple. Small g is equal to Gm upon R square. And therefore, M is equal to GR square upon capital G. Very good. So it is option B. Right? Let's see this one. The acceleration due to gravity G and mean density of Earth rho are related by which of the following relations? Okay. So here the relations are given in terms of rho. So we have the formula G is equal to 4 by 3 pi r rho G, which means rho will be equal to, take that this thing on other side, 3 by 4, okay, then G divided by pi r capital G. Okay, is there such an option? 3G divided by 4 pi G. Right, right. Option A. Okay, so this is also very simple. Next one, radius of Earth is about 6,400 kilometer and that of Mars is 3,200 kilometers. Okay, it is half. The mass of the Earth is about 10 times mass of Mars. An object of weight 200 Newton. Object weighs 200 Newton on surface of Earth. Its weight on surface of Mars will be. So tell me. Let's find out weight on Mars will be equal to acceleration due to gravity. Mass multiplied by acceleration due to gravity on Mars. Okay. So m multiplied by g on Mars is g mass of Mars upon radius of Mars square. And here we can put g will be same. Mass of Mars is given. Okay. Mass of Earth is 10 times. So mass of Mars is mass of Earth upon 10. Okay. So m by 10. 10 I will take here. And radius is 3200. So it is half. So it is r by 2 square. Okay, so we have gm upon r square here, and this thing will become 4 by 10. So weight on Mars will be equal to 4 by 10, or you can say 2 by 5 multiplied by m multiplied by g. Okay, right, mg. So that is 200. So 200 upon 5 is how much? 40. 40 times 2, 80. Okay, so all of these questions are easy. Let's see next one. A body weighs 72 Newton on surface of Earth. What is gravitational force on it at a height equal to half of the radius of Earth? Oh, I think we have solved this. And okay, so it's repeated one. Okay, it's repeated one. Option B is the answer. Okay, same question they have repeated. Let's see next one. A body weighs 200 Newton on surface of Earth. How much will it weigh halfway down the center of Earth? So tell me. Right. Very good. So it will be m multiplied by g at depth d. Okay. So it is m g multiplied by 1 minus d by r. And how much is depth? It is halfway down. That means d is equal to r by 2. So r by 2 upon r is 1 by 2. 1 minus 1 by 2 is 1 by 2. Okay. So this is mg is 200. It is 200 times half, 100. Option A. Okay. Now acceleration due to gravity at height 1 meter, 1 kilometer above the earth is same as depth d below the surface of earth. Then which formula to use? GH is equal to GD. What is GH and what would be GD? In this case, you will use this formula. It is G times 1 minus twice h upon r. Why? Because r is very, very, very small. Okay. GD is, it is always G times 1 minus d by r. So G and G gets cancelled. 1 and 1 will get cancelled. 2h upon r is equal to d by r. R also gets cancelled. 2h is equal to g d, and therefore d is h by 2. Sorry. D is equal to 2 kilometers. It's option C, right? Next one, starting from center of Earth, having radius r, the variation of g. Option B. It is repeated. Okay. The height at which the weight of a body becomes 1/6 its weight on the surface of Earth. Okay. So GH is equal to G by 16, because weight becomes 1 by 16, right? So it is G times R upon R plus H whole square is 1 by 16. Okay. G will get cancelled, right? Times G. So this G will get cancelled. And now if you take square root, it will be 1 by 4. R upon R plus H is 1 by 4. That means denominator is equal to how much? 4R, because then RR will get cancelled. Okay. So r plus h is equal to 4r, and therefore h is equal to 4r minus r, 3r. Okay. Tell me. See, I told you it's repeated many times in various exams. In NEET itself, it is repeated thrice. Okay. Sit option A, dependence of acceleration due to gravity on distance r from center of Earth assumed to be a sphere of radius r and of uniform density. It is this thing, no? Option D, option 4. Yeah, yeah, yeah. Okay, so they have this time they have written 1, 2, 3, 4, and correct figure is A. Okay, which is 4. Good. All right. Next is the effect of Earth's rotation on acceleration due to gravity. Okay. So what happens when Earth rotates? What will happen if something rotates? So because of rotation of Earth, each body on Earth's surface, it will be pulled towards center of Earth, right? So it will need some centripetal force. And what will provide that centripetal force? So which is that thing? It is gravitational force, right? So gravitational force is pulling Earth, okay, but some part of it is going to the it is contributing to the centripetal force, and that's why the normal reaction that we'll feel would be lesser, okay, because some part is going in providing the centripetal force. Okay, so see, now suppose, let's consider this particle, which is at this point particle man having some mass, and now Earth is rotating. So this object will revolve in a circle. It will revolve in a circle like this. So suppose omega is the angular velocity of Earth. Okay. So this particle is pulled towards the center of Earth. Sorry, not center of Earth. Now it will need some centripetal force. Okay. So which will be towards this center, and of course it is pulled by acceleration due to gravity in this direction. The gravitational force acts in this direction, right? So some component of this gravitational force, you can say it will be in this direction, okay, which will provide the centripetal force. And therefore now the effective gravity will be lesser, and we just have to remember this formula that at latitude phi, latitude meaning this angle. So suppose you are on equator, anywhere on equator, then if you cut the Earth along equator, you will get this great circle, okay, big circle, right? Now suppose this is the center of Earth and this is equatorial plane, okay, that great circle is on equatorial plane, okay. So that equatorial plane and the line joining the this object to the center of Earth, they will have some angle between them. It is known as latitude. Okay, so angle between the equatorial plane and line joining the center of Earth to the position of an object, it is known as latitude. Latitude is phi. That angle is phi, suppose. So then at latitude phi, the value of acceleration due to gravity g phi is equal to g minus r omega square cos square phi. Okay, where r is radius of Earth, omega is angular velocity of Earth, and phi is of course the latitude. Okay, so it is g minus r omega square cos square phi. So at equator phi is equal to 0. Okay, and at poles it is 90 degrees. So see, this variation in acceleration due to gravity because of rotation of Earth is maximum at poles because phi is 90 degrees, cos of phi, okay, would be 1, and therefore it is g minus r omega square. On pole, it is 0 degrees, cos 0 is, sorry, at equator, it is 0 degrees, okay. Did I do a mistake here? Let me check. Cos of 0 is 1, right? Oh, I wrote GP and GP only at both places. Okay. So at equator phi is equal to 0, right? And cos phi is 1. Therefore, this variation is maximum at equator. So G at the equator is G minus R omega square because cos of phi will be equal to 1. Okay. So on the equator, it is maximum change because of the rotation of Earth. In what? In acceleration due to gravity is maximum along equator. And on poles, phi is 90 degrees and cos of 90, okay, cos of 90 is 0. So there is no variation on poles. So on poles, the acceleration due to gravity is just equal to g, which is 9.8. Is this thing clear? So then let's talk about the gravitational potential energy. So now we know that if there is any conservative force acting on a body and some work is done against the conservative force, what happens? That work gets stored as a potential energy because we want to do, we want to give some energy to the body in order to do that work. So that work gets stored as a potential energy of the system. Okay. So suppose there is, let's suppose some object which we lift to this height h. So what will be its potential energy? On Earth's surface, we consider that potential energy is 0, and at height h, it will be equal to mgh if height is small, right? But now we have studied that correct formula for acceleration due to gravity is not, it's not equal to g only, okay, 9.8, it varies, okay? So it is gm upon r square. So correct formula for gravitational force is gmm divided by r square. Acceleration due to gravity is equal to what? Gm upon r square. And therefore now we'll find the work done against the gravity to displace an object, and then we'll define potential energy in that way. Okay. So let's suppose you have an object which is at infinity and you bring it at distance r. Okay. And then you find this work done. So what is work done in displacing an object by distance dr? It will be f dot dr, okay, which is gmm upon r square multiplied by dr, right? So you do that, you derive it, and finally you find that the work done is equal to what? Minus of gmm upon 1 upon r2 minus 1 upon r1, okay, right? If it is moved from r1 to r2, work done is equal to minus gmm multiplied by 1 upon r2 minus 1 upon r1, okay. Then you put r1 as infinity and you say that potential energy of an object at infinity will be equal to 0. So as we discussed in case of spring also, and in the concept of conservative forces, what we can do, we can find out change in potential energy only, not the actual value of potential energy. So we define that potential energy at infinity will be equal to 0. So if r1 is equal to infinity, potential energy at r1, which is u at r1, is equal to 0, okay. U at infinity is equal to 0. Then we get the simple formula for potential energy at distance r, and that is equal to what? U of r is equal to minus of gmm divided by r. Okay, so now we take this simple formula, find out change in potential energies when we move some object from one location to other location, one height to other height. Okay, so what is the formula for potential energy of an object? It is equal to minus of gmm upon r. Okay, where g is of course the universal gravitational constant, capital M mass of earth, small m is mass of that object which you are moving, and r is distance from center of earth. Is this thing clear? Okay, we have to remember this formula, that u at r is equal to minus of gmm upon r. Now when r is equal to what? Capital R plus h. Okay, small r is equal to capital R plus h. Then u at r is equal to what? Minus of gmm upon r plus h. Okay, and now there is an important trick which we can use at many places in gravitation. What is that trick? So we know that g is equal to gm upon r plus h square. Okay, g at height h is gm upon r plus h square. So what is gm? Take this thing on other side. So remember that gm is equal to gh multiplied by r plus h square, or g into r square. Okay, so in this formula, u at r, or u at capital R plus h, you put gm is equal to gh into r plus h square. So what happens? This r plus h in denominator and this square gets cancelled out, and you get this formula, minus of gh into r plus h multiplied by m. Okay, so this thing you don't need to remember. This thing you don't need to remember. You just need to remember this formula, and we can always use gm, g multiplied by capital M, as gh into r plus h square, or g multiplied by r square. Is it clear? Okay, and we will be using this. Okay. Next, we define the gravitational potential. So what is gravitational potential? So see, we found work done. Okay, work done in moving an object from infinity to distance r from the center of earth. We found it is minus gmm upon small r. We didn't do the derivation, but we know that it's equal to minus of gmm upon r. So what is gravitational potential at any point in space? It is work done to bring a mass m from infinity to r, okay, to that point, divided by the mass, right? It is work done to bring a mass from infinity to a position divided by that mass. Okay, so the gmm minus of gmm upon r divided by mass, mass and mass gets cancelled. So what is the gravitational potential due to earth at any point r, any point which is at distance r from the center, is minus of gm upon r. Okay, minus of gm upon small r, right? And as I said, we can put gm is equal to gh into r square. Okay, so putting that, you will get gravitational potential is equal to minus of gh into r. Okay, this is clear. Okay, then next let's find out the escape speed. Okay, so what is the speed of an object? Okay, with what speed an object must be thrown from earth so that it escapes the earth's gravitational bound, okay, earth's gravitational influence, and reaches to what? Infinity. Okay, so for that, so see, if object is at distance r, object is at distance r, then potential energy of that object is minus of gmm upon r, right? And now suppose we give it some kinetic energy, and giving that kinetic energy, what do we want to achieve? We want to send it to infinity. Okay, so sum of this potential plus kinetic energy is equal to sum of potential energy and kinetic energy at infinity. Okay, and the sum of potential energy and kinetic energy at infinity will be equal to 0. We don't care if it stops at infinity. Okay, even if it stops at infinity, potential energy is 0, the gravitational force will be 0, so it will not come back, right? So we said the total energy of the object at infinity is equal to 0, and it is sum of potential energy and kinetic energy, right? So then we can move this term on other side, and we can find out this v. Okay, we find out v square will be equal to 2 times gm upon r. That means v, the velocity with which that object must be thrown from distance r from the center of earth such that it goes to infinity. So this velocity is known as escape velocity. That's why suffix e. Okay, because it escapes and never comes back. Okay, so v is equal to square root of 2 times gm upon r, and as I said, we can put gm is equal to gh into r square. So substituting that, you get v is equal to square root of 2 times gh into small r. So either you have this formula for escape velocity square root of 2 gm upon r, or you have this formula v is equal to square root of 2 times gh into r. And if the object is on earth's surface, what will be its escape velocity? So h will be equal to 0, and substituting the values, you will get 11.2 kilometers per second. So if you want to send something at infinity from earth's surface, you have to throw that object with the escape velocity, which is equal to 11.2 kilometers per second. Okay, so suppose you don't like somebody, throw him her with this much speed. Okay, so it will move to infinity and never come back. Is this in clear? Now let's solve some problems based upon these things. R is radius of earth, omega is angular velocity, and gp is the value of g at poles. The effective value of g at latitude lambda equals to 60 degrees is. So this is very simple. gp, g is equal to what? G at poles minus g phi, let's say, r omega square cos square phi. Yeah, cos square 60. What is cos of 60? 1 by 2. So cos square 60 is 1 by 4. So gp minus r omega square by 4. Option A, right? When the rotational speed of earth is increased, then weight of a body at the equator. Tell me. It will decrease because g decreases, and at poles, the body is at poles, g will remain same, so nothing will happen. Okay, so weight at the equator decreases. Next question. The acceleration due to gravity on Earth's surface at poles is g, and angular velocity of Earth about the axis passing through poles is omega. An object is weighted at the equator and at a height h above poles by using spring balance. If weights are found to be same, then h is, tell me, at poles Right. Very good. So GH at pole is equal to G at equator only, not at any height. Okay. So this is G times, and H is very, very small. This is given. So 1 minus twice H upon R. And this one will be G minus, yeah, but at equator it is just G minus R omega square. Okay. Cos 0 is 1. So you have this G. If you multiply this, okay, you have G which gets cancelled with this G. So you have G multiplied by 2H upon R is equal to R omega square. And therefore take these things on other side. So H is equal to R square omega square divided by 2G, right? Option A. So this is also simple. Next question. The work done to raise a mass m from the surface of Earth to height h, which is equal to radius of Earth, is. Tell me. Okay. Work done is equal to change in energy, right? Yeah. So it is, I can say, potential energy at height h minus potential energy on Earth. Okay. So potential energy at height h is how much? Minus of gm small m upon r plus h, and you have minus of minus gmm upon r. So that is equal to, what is h? Equal to radius of Earth. So this is minus of gmm upon 2r, because h is equal to r, plus gmm upon r. So you can take gmm upon r common. It is 1 minus half. That's half. Okay. This is minus half. This is 1. Okay. So it is half of gmm upon r. Okay. And you can put gm is equal to, right, gm is equal to gr square, because in options it is given mgr. Okay. So it is half of g times m, oh, this is gr square, into small m upon r. So this is half of mgr. Okay, option D. So actually once you come to this point, gmm upon r will be equal to mgr. Okay, if you substitute that, gm is equal to gr square, you will get mgr, right? Okay. So next question, at what height from the surface of Earth the gravitational potential and the value of g are minus 5.4 into 10 raised to 7 joules per kg and 6 into, sorry, 6.0 meter per second square respectively. Take the radius of Earth 6,400 kilometers. Okay. So V is equal to minus gm upon r plus h, right? If we are given with acceleration due to gravity, so in place of this gm, we'll put GH multiplied by R plus H square, okay, divided by R plus H. So this thing will get cancelled, and we have V equals to minus of GH into R plus H. So V is minus 5.4 into 10 raised to 7. It's equal to minus of 6 multiplied by R plus H. Okay, let's take that 6 on this side. So 6 nines are 54. This will be 0.9 into 10 raised to 7, or 9 into 10 raised to 7, 6. So R plus H is 9 multiplied by 10 raised to 6. R is how much? 6.4. Yeah, 6400. It is 6.4 into 10 raised to 6. Okay, so H is equal to, oh, H is equal to 9 into 10 raised to 6 minus 6.4 into 10 raised to 6 in meters. Okay, 10 raised to 6 you can take common. So this will be 9 minus 6.4. How much? 2.6. Right? So answer is option C, 2600 kilometers. Okay, let's see next one. Infinite number of bodies, each of mass 2 kg, are situated on x-axis at distances 1 meter, 2 meter, 4 meter, 8 meter respectively from the origin. The resulting gravitational potential due to this system at origin will be. Okay. Let's draw this. Suppose this is the origin, and there are various bodies of mass 2 kg. They are situated on x-axis at distances 1 meter, 2 meter, 4 meter, 8 meter. So what's happening with the distance? Can you guess? 1 meter, 2 meter, then at 4 meter and 8 meters, so on and so forth. Okay, you have these bodies. Okay, so they are keeping those bodies till infinity. Okay, the resulting gravitational potential due to this system. So what will be gravitational potential? V is equal to minus gm upon r for first body, for second body, for nth body. Okay, so mass is same for all those bodies. R is changing, right? So I can take minus gm common, multiplied by 1 upon r1 plus 1 upon r2 plus 1 upon r3, so on and so forth. Okay, r1, r2, r3 will be 1 meter, 2 meter, 4 meter, etc. So that is minus of g multiplied by mass is 2, and how much is r1? 1, r2 is 2, r3 is 4, r4 is 8. Can you guess what is this thing? 1 by 2. Okay, so ratio is 1 by 2, right? This is a geometric progression, GP. Okay, and its ratio is 1 by 2. First term is 1, ratio is 1 by 2. Okay, if you divide this first term, uh, okay, if you divide second term by first term, you will get 1 by 2. If you divide third term by first term, sorry, second term, again 1 by 2. Fourth term by third term, again 1 by 2. Okay, so the ratio is 1 by 2. So how do you find sum of this thing? There is this formula. The sum of GP is given by what? A, which is first term, multiplied by 1 minus r. R is the ratio. Okay, so A is equal to 1 here, and R is equal to 1 by 2. Okay, I guess this formula is there in 10th standard. Okay, APGP is there, right? So 1 minus, I'm talking about CBSE. I don't know about other boards. So this 2, this is 1 minus half. It's half. 2 will go to the numerator, so it will be 2. 2 times this minus 2g is minus 4g. Okay, so this is the answer. Option B. Everything clear? Okay. Let's see next one. Again, you have mgr. A body of mass m is taken from the Earth's surface to the height equal to twice the radius r of the Earth. Change in potential energy of body will be. So tell me, delta U minus gmm upon r. Okay, right. So it is minus gmm upon capital R plus h. Okay, this is final U minus, you have initial U gmm divided by r. So what is h? Twice the radius r. So it is minus of gmm upon 3r plus gmm upon r. Okay, how much is this? It is 1 minus 1 by 3, right? If you take gmm upon r common, this thing is 1, this is minus 1 by 3. So you get 2 by 3. So 2 by 3 times gmm upon r, and this gmm upon r can be written as mgr by writing gm equals to gr square. So which is the option? Option D only, right? So option D. So this is clear. Okay. Next question. A particle of mass m is situated at center of spherical shell of same mass and radius a. The magnitude of gravitational potential at a point situated at a by 2 distance from the center will be. Okay. So there is a particle of mass m. It is at the center of spherical shell of same mass. Okay. You have a shell like this. Its mass is m, and there is a particle at the center whose mass is also m. In the magnitude of gravitational potential at a point at distance a by 2. So you have a point at this much distance a by 2. What will be the gravitational potential? Option B. Why? Gravitational force inside shell is 0, potential is not 0. Okay. See, how will you find the gravitational? What is the relation between uh, this gravitational potential or potential energy and force? What is relation between potential energy and force? Tell me. It is equal to minus of du by dr, right? So if you just want magnitude, it will be du by dr. So now force is 0. That means du by dr is 0. What does it mean? That if you have only shell, okay, inside shell, the gravitational force is 0. That means du by dr is 0. That means u remain constant. U remains constant. Okay. So u is constant. So now you have a mass anywhere inside the shell, okay, you have mass here on the surface of shell or inside shell, its gravitational potential energy will remain constant. How much is that? U minus of gmm divided by r, because if you take just inside shell, it if there is a mass just inside shell, its gravitational potential energy will be equal to minus of gmm upon r. Okay, so just inside shell means almost on the shell. Okay, right? So almost on the shell or just inside shell, there won't be much change in potential energy. So that's why it is minus of gmm upon r. So what would be potential due to shell then? Inside shell, inside shell. It is not changing, it's constant, but how much is it? We know that it is equal to U upon m. Okay, potential energy divided by m. So it is minus of gm upon r. Okay, but here r is equal to a. So now there are two potentials. If you consider this point at distance a by 2, here at this point P, there are two potentials. Okay, so V is equal to V due to shell plus V due to this mass. V due to shell is constant everywhere inside the shell. How much is it? Minus of Gm upon R. Here R is equal to A. It is minus of Gm divided by A. Okay, and potential due to mass. Okay, if you have some mass here, its potential at distance r will be minus of gm upon that distance. How much is this distance? This is a by 2. So it will be minus of gm upon a by 2. So this 2 will go to the numerator. So it is minus gm upon a minus 2 gm upon a. So it is minus 3 gm upon a is the answer. Is it clear? And of course, if you want magnitude, it will be 3 gm upon a. Okay, so this was asked in mains 2011, and I guess this is not mains, this is NEET 2010. Okay, all right. Let's see next one. Tell me answer of this. It is option A. All right. So we know how to solve this question, right? A body of mass m is placed on Earth's surface, which is taken from Earth's surface to height h equal to 3r, right? So what is change in gravitational potential energy? So delta U equals to gravitational potential energy on Earth minus that height, or you can say final gravitational potential minus initial. Okay, final is minus gmm divided by r plus h. H is 3r, so it is 4r plus, no, it will be option C, no? Okay, so it is minus gmm upon r, so that becomes plus. So it's 3 by 4 mgr, option C. Okay, no, you have to substitute that. Okay, all right. Okay, next question. A black hole is an object whose gravitational field is so strong that even light cannot escape from it. You might have seen some movies like Interstellar or something. Okay, have you seen? Interstellar is very good movie. All right, there is a black hole in that movie. There are various Hollywood movies in which black hole they show black hole, etc. Okay, sci-fi movies. Anyways, a black hole is an object. What is black hole? It's an object whose gravitational field is so strong that even light cannot escape. Okay, light cannot escape from it. To what approximate radius would Earth, mass is this much, have to be compressed? How much do you need to compress Earth so that it becomes a black hole? This is a question. Okay, so how much would be escape velocity? If light cannot escape, it is velocity of, yeah, that is the formula, root 2 gm upon r. But how much would be the value? 3 into 10 raised to 8, right? So then we can put v is equal to 3 into 10 raised to 8, and we have square of that is equal to 2 times gm upon r. Okay, so 2 times g is how much? 6 into 10 raised to sorry, mass is given. Oh, they didn't give g. I guess it is 6.67 into 10 raised to minus 11. Okay, so 6 into 10 raised to 24 is mass of Earth divided by r is 6,400 kilometers, or 6.4 into 10 raised to how much? 6. Okay, radius of Earth 6,400 kilometers, or 6.4 into 10 raised to 6 in meters. Okay, yes, no. So we'll do some round figure calculations here. So this thing I will just cancel out, 1.1 or something. Okay, this thing will be 1.1 or something, but we just want order of magnitude, so it doesn't matter. We'll just cancel it out. Then we get, this is 9 into 10 raised to how much? 16. 10 raised to 16. Oh, no, 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 no. Oh, I did a horrible mistake here. How much should Earth be compressed is a question. So we cannot cancel it out. I'm sorry. I substituted values this side, that side. We want to find something, right? We want to find R. Okay, we cannot substitute R. I'm sorry. So it is 3 multiplied by 10 raised to how much? 8 square is equal to 2 gm upon R. We want to find R. Let's keep R as it is. Into 2 multiplied by G is 6.67 into 10 raised to minus 11. And you have mass of Earth 6 into 10 raised to 24. Okay. All right. Then this is 9 into 10 raised to 16. Okay, let's move R on that side. You have R is equal to, this is 6 square. I will take 46, almost. More than that, you can take 40 because this is 6.67. So round figure, it is 2 times 40 into 10 raised to how much? 13. 24 minus 11. Okay. And in denominator, you have 9 multiplied by 10 raised to 6. 16. So this will become 10 raised to minus 3. 10 raised to minus 3. And this is 80 by 9 or 90 by 9. I can say this is almost 10. Okay, near about. So this 10 multiplied by 10 raised to minus 3 of the order of 10 raised to minus 2 is the answer. So if you keep mass of Earth as it is and radius of Earth is made equal to what? 10 raised to minus 2. then Earth will become black hole. Okay, 10 raised to minus 2 meters. Got it? Yes, no? Okay. All right. Let's see next question. The radius of a planet is twice the radius of Earth. Both have almost equal average mass densities. Vp and V are escape velocity of planet and Earth respectively then. So both of them have almost equal average mass densities. This is given, and radius of planet is twice the radius of Earth. So tell me, in where is inversely proportional to R? No, see, what is given, radius of a planet is twice the radius of Earth. This is given. And both have average mass densities. So density is equal. And you are asked to compare the escape velocities. So escape velocity of a planet divided by escape velocity of Earth will be equal to, so now you have this formula. You have two formulas. Square root of 2 gm upon R. This is one. And if you put gm equals to gr square, you have this another formula, square root of 2 gr. Okay. Which one should we use? This one. Why? Because mass is given. Okay, mass density is given. We can substitute g. G is equal to 4 by 3 pi r rho g. Right? Okay. So this is square root of 2 g for the planet, r for the planet, divided by square root of 2 g for Earth. Okay, or let's keep it as g and r. So this will be equal to, then let me keep 4 by 3, 2 will get cancelled. Pi r rho g. Okay, so this is for planet, rho for the planet, g is same, and this is r for planet. And in denominator you have 4 by 3 pi r rho g multiplied by this r. Okay, I have just substituted g. So now see, lot of things get cancelled out. This thing gets cancelled out. Density is same, so it gets cancelled out. G gets cancelled out. So you have radius of planet square upon radius of Earth square, right? So that is, if you take square root, it will be just radius of planet upon radius of Earth. Yes. Right. You have square root, take square. You have square, take its square root. Okay, it will be just Rp upon R. And what's that? It is just 2. Rp upon R is equal to 2. That means escape velocity on planet is twice the escape velocity on Earth. This is the answer. Option B. Is it clear? Okay, let's see next one. Particle of mass m is kept at rest at height 3r from the surface of Earth, where r is radius of Earth and m is mass of Earth. The minimum speed with which it should be projected so that it does not return back. Okay, tell me. Particle of mass m is kept at rest at 3r from the surface of Earth. Okay, at 3r from the surface of Earth, where r is radius of Earth and m is mass of Earth. Now, what should be its minimum speed so that it does not return back? So that means it goes to infinity. Okay, so see, you have potential energy at height r plus kinetic energy at height r is equal to potential energy at infinity plus kinetic energy at infinity. Yes. So this thing will be equal to 0 because it will go to infinity. We want just enough energy so that it reaches infinity. At infinity, its velocity becomes 0. We don't care. Okay. Actually, we want just minimum energy with which we should throw it. That means its kinetic energy at infinity will become 0. Okay. Right. We'll take this term as 0. Potential energy is already 0. It will go to infinity and stop. Okay. So its kinetic energy is also 0. Right. So how much is UR? It is minus of GMM upon small r, which is capital R plus H, plus half of mv square is equal to 0. Gets cancelled. Then you have v is equal to how much? V square will be equal to 2gm upon r plus h. So 2gm upon 4r. Right. So this you can take 1 by 4, square root of 1 by 4, that will be 1 by 2. Okay. This is just escape velocity at height h. So you can directly use this formula, v equals to square root of 2gm upon r plus h. Okay. So instead of doing all this, so right, then you get it is equal to what? 1 by 2 multiplied by square root of 2gm upon r, and put gm equals to, no, options are uh, gm upon 2r raised to half. Okay, this is the distance from surface of earth. Which one is correct? This one is correct, right? We don't need to take it outside, just put, okay, we got this v equals to 2gm upon 4r, and this can be written as 2gm upon 4r raised to half. Okay, and gm is equal to gr square, so it will be 1 by 2. Oh, it will be 1 by 2 multiplied by gr raised to half. So if it is, yeah, if it is this thing in terms of gm upon r, is it option B? No, I don't think so. This one is correct, no? Option A. Yeah. It's option A. Okay, 2 by 4 is 1 by 2. What was I searching for? Option A is correct. Okay, all right. So you don't need to do this recipe. You have that. You have direct formula. Okay, just use that. Okay, just use that and put h is equal to whatever is given. Okay, h is equal to 3r in this case. So it will be square root of 2gm upon 4r, right? So we get this answer. Okay, let's see next one. A particle of mass m is thrown upwards from the surface of Earth with velocity u. The mass and radius of Earth are, respectively, m and r. G is gravitational constant and small g is acceleration due to gravity on surface of Earth. The minimum value of u so that particle does not return back. So they are asking about escape velocity. How much is it? Root 2 gm upon r. Right. Next one. Earth is assumed to be a sphere of radius r. A platform is arranged at height r from the surface of Earth. The escape velocity of body from this platform is Fv, where v is escape velocity from surface of Earth. The value of F is, okay, so escape velocity at height h with respect to escape velocity on Earth, it will be square root of, yeah, Earth surface, square root of 2gm upon r plus h, and I want to divide by this, so it is multiplied by its reciprocal, so it is r divided by 2gm. So this thing will get cancelled out, so it is just r upon r plus h. How much is it? H is how much? You know, r by 2. Okay, so it is r by 1 by 2, right? This is h is equal to r, so it is 1 by 2, root of 1 by 2. Okay, because h is r. So escape velocity at this height is given, it is Fv. How much is escape velocity on Earth? It is equal to v. And how much is this factor is asked. Okay, so v gets cancelled. You get F equals to 1 upon root 2, or root of 1 by 2, or 1 upon root. Option C. Okay, all right. Another one, with what velocity should a particle be projected so that its height becomes equal to radius of Earth? Tell me. So, see, what will happen, its total energy on Earth should be equal to total energy at that height, right? If you throw some object, it goes to some height, then its total energy on Earth is equal to total energy at that height, right? So, how much is total energy on Earth? Is total energy at that height, whatever is the height. Okay. So, at that height, it reaches to maximum height, means kinetic energy becomes zero. Total energy is just potential energy, and then that is minus gmm upon r plus h, right? So it is minus of gmm upon r, this is potential energy, plus you have kinetic energy, and you want to find out velocity, it is half of mv square. Okay, take this thing on other side, h is equal to r, you have half mv square is equal to, this will become positive gmm upon r minus gmm upon 2r. So this is gmm upon 2r, right? Gmm upon r minus, this is gmm upon 2r. Okay, so it is gmm divided by 2r. 1 minus half is half. Okay, so half mv square is equal to gmm upon 2r, and this 2 gets cancelled, gets cancelled, v square is gm upon r. So v is equal to square root of gm upon r. Okay, it's option A. This is clear. Okay, good. Another one, for a planet having mass equal to mass of Earth, but radius 1/4 of radius of Earth, the escape velocity of the planet will be. So tell me, escape velocity is equal to, mass is same, but radius is 1/4. Okay, radius, it will be mass of planet, radius of planet. Okay, this is escape velocity. Put the values. Mass is equal to mass of Earth, 2 times gm. Radius is 1/4, r by 4. Okay, and that 4 will go to numerator. So this is equal to square root of 4 times 2gm upon r. Square root of 4 is 2. So V is equal to 2 times root of 2 gm upon r. Yeah. So it is 2 multiplied by 11.2 kilometers per second. So that is 22.4 kilometers per second. Option B. Okay. All right. Then we'll discuss satellite. Okay. Okay. So now anything which revolves around Earth can be called a satellite. So we have one natural satellite, which is Moon, and there are some artificial satellites. Okay. But for anything to revolve around Earth, we need some centripetal force, and that centripetal force is provided by what? The gravitational force due to Earth. Okay. So now if you put centripetal force is equal to mv square upon r, okay, and gravitational force is gmm upon r square, you get v square equals to gm upon r, and therefore v is equal to root of gm upon r, small r, which is capital R plus h. So this is the formula for orbital speed of a satellite. Okay, considering that satellite revolves around Earth in circular orbit, we'll find we find the orbital speed of the satellite, and it is equal to root of gm upon r. Okay, small r, which is equal to capital R plus h. So this is formula for orbital speed we need to remember. Then we can put always gm is equal to small g into r square, or gh into small r square, which is capital R plus h square, and we get this another formula, which is equal to square root of gh into r. Okay. Then now v is equal to 2 pi r upon t, because in one revolution the distance covered will be equal to 2 pi r. Time period is t. Okay, time period of the satellite is t. So substituting that, we get t square is equal to this thing, 4 pi square r cube upon gm, or t equals to 2 pi multiplied by square root of r cube upon gm. Okay, this is the formula for time period of a satellite. We need to remember this formula too. Okay, and here you can see that t square is equal to 4 pi square upon gm multiplied by r cube. This thing is constant, this thing is constant, so t square is directly proportional to r cube. What is this thing? It's Kepler's law, right? This is Kepler's law. Kepler's law of planetary motion. So just like moon is satellite of Earth, we can say Earth is satellite of sun, or every planet is satellite of sun. Okay. So what will be time period of Earth or any planet around sun? It is 2 pi multiplied by square root of r cube upon gm. Okay. And here m is mass of sun. Okay. This is mass of that thing around which your satellite revolves. So this is mass of sun, and r is, it is semi-major axis, or the average radius of the planet around sun in that case. Okay, and t square is directly proportional to r cube. It is proved like this. Okay, it was proved by Newton. Okay, so see, if you take this form of gravitational force, you can prove the Kepler's laws. Okay, is this thing clear? Okay. Now let's come to energy of a satellite. So see, what will be total energy? Potential energy plus kinetic energy. Okay, kinetic energy will be equal to half of mv square, where v is equal to root of gm upon r. You put that, so you get total energy is equal to minus of half of gmm upon r. So now you can compare this total energy with potential energy and kinetic energy. First of all, as we discussed in last class, the total energy of a satellite revolving around Earth will be negative, or total energy of a planet revolving around Sun will be negative. In case of any bound system, the total energy is negative, and you can see that here. It is minus of half of gmm upon r. Okay, so in any bound system, total energy will be negative. Then this total energy is equal to half of potential energy. Okay, it is take half of potential energy is how much? Minus of gmm upon r, and total energy is minus of half of gmm upon r. So it is half of potential energy. Okay, so this is one relation between total energy and potential energy of a satellite. And another relation is if you take kinetic energy will be equal to, so here you have found the kinetic energy. Okay, it's half mv square. So it is just equal to half of gmm upon r, and total energy is minus of half of gmm upon r. So what is relation between total energy and kinetic energy? The relation is total energy is negative of kinetic energy. Kinetic energy will be always positive. Total energy in bound system will be negative. So total energy is minus of kinetic energy. Is this thing clear? So then next is binding energy. So what is binding energy? So the energy which must be given to satellite so that escapes the Earth's gravitational bound. It is known as binding energy. Okay. So now you can say the satellite is bound with Earth with this much energy. It has got this much negative energy. So if you give this much amount of positive energy to the satellite, then what will happen? It will escape. Okay. How do you give that energy? You give it some velocity. So it will escape the Earth's gravitational bound. How much energy is required? This much energy is required. Okay. So binding energy is equal to what? It is plus positive half of gmm upon r. Binding energy is equal to negative of total energy. Okay. And now the escape speed required for a satellite. Okay. Kinetic energy of escape, the energy that you give is in form of the kinetic energy. It is in form of the speed. Kinetic energy of escape will be equal to this binding energy. Okay. So by doing that, you find the escape velocity of a satellite, and it is equal to square root of gm upon r. Okay. Escape velocity of revolving satellite. It is already revolving around Earth with speed of square root of gm upon r. How much more velocity you want to give it? You need to give it so that it will escape. It is square root of gm upon r. Okay. So this is for the revolving satellite. Okay. So in case of revolving satellite, the escape velocity is just equal to its orbital speed, and orbital speed is also known as critical velocity. Okay, orbital speed is also known as critical velocity. Okay, this is also known as critical velocity of satellite. Okay. So is there any problem till this point? Now, if satellite is resting on Earth's surface, then how much would be its escape velocity? So its escape velocity will be just equal to root of 2 gm upon r. It is just same as that of any object resting on Earth. Whether it is satellite or whether it is some other object, it does not matter. So on Earth's surface, it is equal to what? Square root of 2 gm upon r. And what is relation between this escape velocity on Earth's surface? Okay, this thing, wordings are important here. Escape velocity on Earth's surface and the critical speed of satellite. Relation is V is equal to root 2 times Vc. Okay, because Vc is equal to square root of Gm upon R. Okay, so we need to be careful regarding what is asked. Okay, and there is one category of satellites which is known as geostationary satellite. So what is geostationary satellite? When you look from Earth towards that satellite appears to be at rest. That means you see that satellite, today it is at some location, tomorrow it will be at same location, day after tomorrow it will be at same location. So how can this thing happen? If Earth rotates and satellite revolves in the same time taken by Earth to rotate, complete one rotation, and time taken by satellite, complete one revolution, if it is equal, then this thing can happen. Okay, so the time period of this geostationary satellite is 24 hours because Earth completes one rotation in 24 hours. Okay, and using this time period, you can substitute this time period here. You can put G, you can put mass of Earth, and the small r is equal to what? Capital R plus H. We can find out height of the geostationary satellite. Okay, so height I don't remember. Uh, okay, so we can find that height and I will write it down here. Okay, all right. So moral is height of geostationary satellite is fixed. Okay, height of geostationary satellite is fixed because time period is 24 hours. M is mass of Earth, G is the universal gravitational constant, R is radius of Earth. There is only one unknown in this equation, that is height. Okay, if you put values of all other things, you will get one value of height. Okay, so height of the geostationary satellite, it is fixed. It has got a fixed value. Is this thing clear? Yes, no? Okay, so it means that you cannot have a satellite cannot be geostationary at arbitrary heights. Okay, right? So a satellite cannot be at any arbitrary height and be geostationary. It cannot be stationary with respect to Earth. This is the meaning. Okay, now let's solve some problems based upon satellites. So see this problem. The time period of a geostationary satellite, it's 24 hours at a height of 6 times of RE. Okay, it is 6 times of RE. RE is radius of Earth from surface of Earth. Time period of another satellite whose height is 2.5 RE from surface will be. So tell me, time period is given. What will you do? V square proportional to R cube, right? So you want to find out T2, you are given with R2. Okay, so T2 upon T1 square will be equal to what? R2 upon R2 by R1 cube. Okay, but what is this R2? It is R plus H2. Okay, and this is R plus H1 cube. Their heights are given. This is 6 RE, this is 2.5 RE. So RE is radius of Earth. We can put those height. Yeah, so this is R plus 6R. So this will be 7R, and this is R plus 3R, 3.5R. R plus 2.5R is 3.5R, and we have cube of this. So RR gets cancelled. It is 7 divided by 3.5 cube. That is 2 cube 8. Okay. So we have T2 upon T1 square is equal to 8. That means T2 upon T1 will be square root of 8. Square root of 8 is 2 root 2. Okay, take T1 on this side. Yeah, so that is 24. So T2 is equal to 24 times 2 root 2 of 48 root 2. Oh, did we do some mistake? We did the opposite way, right? Okay. T2 was 2.5. That the thing that we need to find. Actually, it is 24 hour for this height. So let's take T2 is equal to 24. Okay, and T1 is what we need to find. Okay, 24 divided by T1 will be equal to what? 2 root 2. Got it? Okay. T1 is equal to 24 upon 2 root 2, and that is equal to 12 root 12 divided by root 2. Okay, it is 12 divided by root 2. Okay, this is 6 root 2, right? Okay, this is 12 upon root 2, 6 root 2. This is the answer. Option A. Okay, all right. Let's see next one. A remote sensing satellite of Earth revolves in a circular orbit at height of 0.5 into 10 raised to 6 meters above the surface of Earth. If radius is 6.38 into 10 raised to 6 meters and g is this, the orbital speed of satellite is. Tell me, what can you do? So this is just calculation. What is orbital speed? Square root of gm upon r plus h, small r, which is r plus h. So that is 6.67 into 10 raised to minus 11. Okay, can we do something? Small g is given. So let's convert this. Small g is given. So this is g into r square upon r plus h. Okay, and height is 0.25 multiplied by 10 raised to 6. Okay, so what can we do? 9.8 multiplied by r square, 6.4 into 10 raised to 6 square divided by, it is 6.4 plus 0.25 into 10 raised to 6, right? Okay, then square root of, all right, so v is equal to, we can take this thing outside, 6.4 into 10 raised to 6, because we have square of that. Okay, and this thing also, it is 10 raised to 6, so we can take it outside. It will be 10 raised to 3 in denominator, and then we are left with 9.8 upon 6.4 plus 0.25, so 6.65, right? How much would be this? Well, it will be 1.2 or 1 point something. This is close to 7, this is close to 10. Okay, 10 by 7 is 1.3 something. So square root, see, square root of 1.41 is 1.21, we know. Okay, so if this is close to 1.4, square root is close to what? I'm sorry, square root of 1.21 is 1.1. Okay, square root of 1.44 is 1.2. Okay, so this doesn't seem to be 1.4 or 1.5, because this is close to 10 and this is close to 7. Okay, 7 plus, yeah, it's close to that. Okay, it's close to 1.44. So I can take, this is nearly equal to 1.2. So you have 6.4 into 10 raised to 6 multiplied by 1.2. Okay, close to that. So this will be greater than 6.4. Okay, that is greater than 6.67. Will it be this thing? Yeah, it will be near about this thing, 7.76. Okay, this is my bet. All right. Yes, no. Can you do something better in NEET exam? Okay, I have done some round figure calculation. Okay, I think this is the answer. You can check it, but this is just calculation. Okay, this is just calculation. V is equal to square root of gm upon r plus h. Because of small g is given, we are putting square root of g into r square. Okay, that's it. Gm equals to g into r square. Is this thing clear? Okay. Is this thing clear what I did here? Yes or no? Okay, this is close to, see, this is close to 7 I have taken, and this is what will be 7. Uh, I'm saying what will be 7 plus half of 7, because 7 plus half of 7 is 10.5, right? So I'm increasing this thing uh, by something, okay, some little amount. And if I increase this thing also by little amount, I get 10.5, okay, divided by 7. Okay, so I'm doing some guessing here, okay, some calculation. So this thing will be nearly 1.5, 1.4 to 1.5 of this thing, and therefore if this is 1.4 times this thing, then its square root will be equal to what? 1.2. Okay, what did I write here? Square root of 1.44 will be 1.2. So that's how I have taken the square root, 1.2. Okay, so yeah, uh, we need to do some round figure calculations, and if options are little bit far, which are in this case, we'll guess the correct one. Okay, so I think this one is correct. You can check it afterwards. All right, let's move on to the next problem. The satellite S is moving in elliptical orbit around the Earth. The mass of satellite is very small compared to mass of Earth. Then option A, the linear momentum of S remains constant in magnitude. Option B, the acceleration of S is always directed towards the center of Earth. Option C, the angular momentum of S about the center of Earth changes in direction, but its magnitude remains constant. Option D, the total mechanical energy of S varies periodically with time. Tell me. Linear momentum, does it remain constant? It is moving in elliptical orbit. So in elliptical orbit, what happens? Velocity is not constant. Okay. In elliptical orbit, velocity is highest when it is closest to the planet. If this is planet, when satellite is here, its velocity will be highest. It will be lowest when it is here. So linear momentum does not remain constant because velocity changes. Does the angular momentum remain constant? Yes, we have discussed it. The angular momentum remains constant, and they are saying it changes in direction. So it does not change in direction also. Okay. Is the acceleration always directed towards the center? Yes. Okay. Acceleration is always directed towards the center, right? So it is option B. And total energy. varies periodically with time. So total energy does not change. Okay. If kinetic energy increases, potential energy will decrease. If kinetic energy decreases, potential energy will increase, but total energy remains constant. It does not change. Okay. So this one is not correct. This one is correct. Okay. Good. Let's see next one. A geostationary satellite is orbiting the Earth at a height of 5 r above the surface of Earth. R being radius of Earth, the time period of another satellite in hours at height 2r from the surface of Earth is. So this is similar to the first problem that we solved. Okay. This time, yeah, let's take T2 by T1 square equals to R2 by R1 square, or R plus H2. Yeah, R plus H2 upon R plus H1 cube. Okay, of course, cube. So this is equal to how much is, okay, which one do we need to find? So time period of another satellite which is at height 2r. Let's keep H2 equals to 2r. Okay, so this will become 3r, r plus 2r, divided by, you have r plus H1. H1 is 5r, so this is 6r, and you have cube of that. T2 upon T1 is 24 hours. Okay, so you have 1 by 2 again. So it's same as that of last one. 1 by 2 cube, 1 by 8. Okay, so T2 will be, take square root. This will be, okay, so this will be 1 by 8. Take cube root. Oh, last problem, did we? Okay, this is T2 upon T1. T2 upon 24 square will be equal to 1 by 8. Now take square root of this. T2 will be equal to how much? T2 upon 24, it will be 1 upon 2 root 2. So move 24 on this side. So it is T2 equals to what? 24 upon 2 root 2. Again, answer is also same as that of last problem, right? So it is how much? 24 by 2 is 12. 12 upon root 2, or 6 root 2. Okay, 6 root 2 hours. Option C is the answer. Simple. Okay, next question. If V is escape velocity and VO is orbit velocity of satellite for orbit close to Earth's surface, then these are related by, tell me. V equals to square root VO, right? Good. It's option D. Next one, radii of circular orbits of two satellites A and B of Earth are 4r and r respectively. The speed of satellite is 3v. Then the speed of satellite B will be. Tell me. So what is the formula? V is equal to square root of Gm upon r. Okay. Not this r. Yeah. Small r. Okay. So radii of circular orbits are given. For first one it is 4r. Second one it is r. So we can say V1 upon V2. We want V2. So V2 upon V1 will be equal to root of. It's inversely proportional to root of R. So will be R1 upon R2. Okay. How much is R1? R1 is 4R. How much is R2? R2 is R. So V2 upon V1. Okay. And how much is V1? It's 3V. Take that 3V on this side. This R will get cancelled. You have root of 4, that's 2. So V2 equals to 2 times of V1, that is 2 times of 3V, so it is 6V. Okay. So most of these questions are simple. See next one. A ball is dropped from spacecraft revolving around Earth at a height of 120 km. What will happen to ball? Option A, it will fall down to the Earth gradually. Option B, it will go very far in space. Option C, it will continue to move with the same speed along the original orbit of spacecraft. Option D, it will move with the same speed tangentially to the spacecraft. Tell me. Okay. Its answer is option C. It will keep on moving in the circle, right? Okay. Because when you release that ball, what will happen? So suppose this is Earth, here is your satellite, and you release a ball. Okay. So let's make everything smaller. So satellite is revolving in this orbit. Sorry. Let's suppose satellite is revolving in this orbit. Okay. So now this ball and the satellite both have same velocity. So actually when you release that ball, if Earth was not there, it would have moved in tangential direction, but Earth is there. So ball will try to move in this direction. Okay, every body continues to be state of rest or of uniform motion. Okay, so ball will keep on moving in this direction, but there is Earth which will pull it towards the center, and because of that, trajectory of that ball will become circle. Okay, is it clear? Right. Let's see next question. Satellite A of mass m at distance small r from the center of Earth. Another satellite B of mass 2m is at distance 2r from the Earth center. The time periods are in the ratio of. So this is very simple question. Okay. First is at distance r, second is at distance 2r. So t square is directly proportional to r cube. Okay. So t1 by t2 square is equal to r1 upon r2 cube, and that is equal to, first is r, second one is 2r. So this is 1 by 8. Okay, and therefore t1 by t2 is equal to 1 upon 2 root 2. Option D is the answer. This is clear. Okay, let's see next one. Satellite of mass m orbiting the Earth at height h from its surface. The total energy of satellite in terms of g naught, value of acceleration due to gravity, at Earth's surface is. Tell me, how much is total energy of a satellite minus of GMM 2R. Okay, 2R, which is 2 small r, which is capital R plus H. Okay, is it given in terms of this? They are given, options are given in terms of G naught. Okay, so put GM equals to G into R square, and they are calling it G naught. So let's call it G naught. So what do we get? It is minus of G naught into R square into M upon 2 times R plus H. So which one is correct? Option B. Right. It's simple. Let's see next one. The additional kinetic energy to be provided to a satellite of mass m revolving around a planet of mass capital M to transfer it from circular orbit of radius r1 to another of radius r2. R2 is greater than r1 is. Tell me how much is additional kinetic energy required. K is equal to, or delta K is equal to final potential energy minus the initial potential energy. Okay, so minus of gmm upon r2 minus of gmm divided by r1. How much is this? So which of the options is correct? This will be plus. So it is gmm upon multiplied by 1 upon r1 minus 1 upon r2, right? It's option B. Okay, this is simple. Okay. Let's see next one. Two satellites of Earth, S1 and S2 are moving in the same orbit. The mass of S1 is 4 times the mass of S2. Which of the following statements is true? Tell me. Potential energies of Earth and satellite in two cases are equal. S1 and S2 are moving with the same speed. The kinetic energies of two satellites are equal. The time period of S1 is 4 times that of S2. Tell me. Which one is correct? They are moving. No. Potential energies will be different because potential energy depends upon mass of Earth as well as mass of satellite. Okay. Sorry, I wrote extra 2. Minus gmm upon r. So speed does not depend. V is equal to square root of gm upon r, where m is mass of the Earth only. Here speed will be same because it is square root of g multiplied by mass of Earth divided by r. Okay, if orbit is same, that means r is same. Mass of Earth is same for both of them, so speed will be same. So it is option B. Okay. Or a satellite moving in an orbit around Earth, the ratio of kinetic energy to potential energy is. Tell me. Right. Option A. Okay. When satellite of mass m is orbiting around Earth in circular orbit with velocity v, what will be its total energy? So kinetic energy is half mv square, and we have seen what's the relation between total energy and kinetic energy. Yeah, but it is minus of kinetic energy. Okay, so it is option D, right?